Good morning. We're going to do the part 4 of our robots and marbles tutorial today, the most complex version we've done yet. And as you remember from last video, video 2, we did a live code, which go back and see that one if you'd like to see kind of how we built up the configuration file. And then in the last version, we introduced 2 robot arms instead of 1, adding some of the behavioral aspect and how asynchronous actions occur. So sometimes your 2 actors in a system don't do things at the exact same time. There's time lags. We introduced that feature last time. In this video, we're going to be adding some randomness. Everything to this up until now has been defined. Like this is what's happening and this is what's happening, this is what's happening. In this video, we're going to add some probability and some randomness, some, or as we call stochastic nature to our model. Which will add a little bit more real world complexity. As you can see, we've started very simple and we've been gradually adding more aspects to make this more like the real world as we're building a complex system. So as you can see, and we're using the same model we did last time, which has the robot arm 1 acts on 1 time step, every 2 time steps, robot arm 2 acts every 3 time steps. But here we're giving, we're going to have a 50% chance it will act in every given time step and 33% chance. So we're adding some probabilities here of when the arms are actually going to operate. So before we run that, let's pop under the hood to our configuration file and kind of see what's going on here. So what we're adding here, we're adding some probabilities. So we're adding, instead of we had 1, every 2 and every 3 last time. Here we're adding probability. We're adding numpy random. This is a uniform distribution from 0 to 1. So every time you run this, it's slightly different. And we're having that is the robot probability greater than that for each of these. And it's using the first part of the list or the second part of the list here. So we're adding that randomness of when it's going to operate or not. So we're drawing a random number, see if it's smaller than the robotic arm, and it will act. So that, besides that, everything is the same. We're just adding the mechanism the same, how we wired it up is the same. Everything's the same except we're adding probabilities here, and we're adding the random distribution here from 0 to 1, the uniform distribution. So that's a pretty simple calculation there. Difference, we only incremented it slightly. And then when we run this, the results are a lot different than last time. If you see, this is a different result. But because this is random, let's run it again. I need to run everything here to catch us up. Here we go. Okay, see, that's different than the first time we run it. And we're going to run it again, and it's different again. So you can see between these 2 different results, see how the arcs are different? It's because we're this randomness effect. Let's try it one more time. We're adding this stochastic. Oh, there we go. It's different again. Every time we run this, it looks a little different, which is good. And now it's tighter here than it was last time. We're adding that random component, which makes it more like the real world. So essentially what we're doing is we're defining, and you can use any probability distribution you want to use for this. We like to use fat-tailed normal usually for have more example of extreme events, even though we're normally in a set band with the normal distribution, the bell curve. We like to have fatter tails than usual to have more chance for the farther 6 sigma events, because they're more likely to happen in the real world than the normal distribution usually has. But you can add these components around any of your different properties in your models to allow more variability to affect real world. And then that's why you want to, the next step we're going to talk about is the Monte Carlo runs. So the Monte Carlo run is essentially, it came from Monte Carlo Casino. As you know, most probability textbooks and things talk about casinos and probabilities and things like that. It's kind of how probability theory, one of the ways it was been refined, even though it's very sterile and doesn't act that way in the real world. But the Monte Carlo runs is essentially you roll a dice 50 times and see what the average result is. So essentially, once we have this random state here, what is the average of ooh, that's a lot different that time. And that one's different again. What's the average? If we did this 50 times and averaged it, ooh, they don't even converge at all this time. See, we have a lot of different results, and your real world systems will have this. Traditional forecasting, we're going to look at one process. We're going to look at what happens 50 times. So all we have to do back from our other process is we just change, this was 1, we change it to 50 right here, and this says we're going to have 50 Monte Carlos. It's very, very easy to run 50 Monte Carlos in cadCAD. All we're doing, we can have essentially 1,000 Monte Carlos. You're only constrained here by your processing power. So when we run this, let's see what happens when we run this. Okay, we see the 50 different runs here, and now we're going to plot them. See what happens. Now we're going to make it into a single chart. And we're going to take, so this right here is the results. This is the median results. This is what it looks like when you look at every single result. It looks at something crazy like this. Then we take the median here. Now let's look at the edge cases. And we see edge cases here. So there's, as you can see, there's a lot of variability, but this is the average, the median anyway, which in this case, median is better to do than mean because mean has more of those edge cases. Median just will take what's the middle of our results. We want to get rid of the edge cases in this, and that's our example. It does hit, and it's a little different than when we came up here and we ran results different times. This is looking at 2 different runs. This is just looking at 2 runs. Run 1 and run 9 is what we're doing here. Then when we look at this run is when we see that each individual run, and then when we take the median, whoa. What we need to do here is we have a different configuration file. So we run this again. And there we go. So we'll run this whole notebook one more time to illustrate the difference, because we have 2 configuration files here, one that's Monte Carlo and one that's not Monte Carlo. So as we're rerunning the results here, okay. So this is the result when we run it once. That's one result. And then this is another one where you have this weird action here. And then when we have the 50 Monte Carlos, this is run 1 and run 9 here, run 1, run 9. And then we look at the median is here. It's a lot smoother in the median. And then we look at our edge cases, which never even meet. So as you can see, when you're starting to analyze systems, when you run it with some stochastic properties, and you can imagine when you have a more complex model with these types of stochastic processes throughout to represent the randomness of many different events, this is where you get the dynamic systems, where you have the emergent properties, where how these individual parts interact form something completely different than what was expecting, because all these random processes feeding on top of each other. And that's where you start getting the real power of what cadCAD can do when you start adding Monte Carlos, and then when you do all of the different testing. So hopefully this video was helpful. Always ping us on a Telegram if you have any questions, and we'll be back soon with some more videos. Thanks.